Hello, so this is section 1.6, which is all about, I'm probably going to say this wrong, de Moivre's theorem. Please, yeah, anyway, I need to check that with somebody. Okay, so this theorem says that z to the n is equal to r to the n cos n theta plus I sine n theta equals r to the n ei n theta when z equals r ei theta. This should not come as too much of a surprise, since we've already discussed how angles add and moduluses get multiplied. So the proof, this is going to be by induction. Okay, so the n equals 1 case, z to the 1 equals r to the 1 times cos 1 theta plus I sine 1 theta equals r1 ei1 theta, which of course is z equals cos theta, which we know is true by definition. So its statement is true for true for n equals 1. Right, so let's assume true for n minus 1. Then r to the n, z to the n equals z to the n minus 1 z, which equals r to the n minus 1 x I n minus 1 theta times r ei theta, which we know from the way in which our manipulations work is r to the n ei n theta. Well, kind of. Because I never set up here where n is from. What I've proven is that this is true for n, an element of the natural numbers, because I've proven it for 1, and I've proven it when there's a 1 number difference between n and n minus 1 and n. And so that means the natural numbers. So for example, I have not proven that this statement is true for a half. It is true for a half. This theorem is true when n is a half, or any number, really. Prove it. I've done it for induction on the natural numbers. If you want to prove it for for all of r, then a little more work is needed. So you can do that though. And I kind of cheated anyway, because I implied n is usually a symbol that indicates an integer, so I kind of cheated by using it, because I maybe made some of you think that n was an integer just straight off the bat. Fair cop. Some mathematicians complain bitterly about that. Freezing of symbols is what they call it. Okay, an example. Minus 2 plus I to the power of 10. So first we convert this to polar coordinates. So the modulus of, z equals minus 2 plus 2i. Right, so the modulus of z is the square root of 2 squared is 4, 2 squared is 4, so this is 8, and that is 2 times the square root of 2. And if we draw a little diagram, where does z sit? There's minus 2 real and 2 complex, so it's up here. I know that this is 45 degrees, so that means that theta is equal to 3 pi over 4. So z is equal to 2 square root 2 ei 3 pi over 4. So z to the 10 is equal to 2 to the 10, 2 to the 5, because the square root is a half, EI 30 pi over 4. Okay, now, so that is an argument. And if you left it there, you'd be technically correct, which is, according to some, the best kind of correct. But let's do better. We want the principal argument. Right. Okay, so we need to take out all the powers of all the integer multiples of 2 pi in here. So 30 pi over 4 is equal to 2 pi times 15 over 4, which is equal to 2 pi times 12 over 4, and I've picked that out because it's 3, plus 3 over 4. So that's 3, so that's 6 pi. Well, let me write it as 3 times 2 pi plus 6 pi over 4, which is equal to 3 pi over 2. Okay, so 3 pi over 2, pi over 2, 2 lots of pi over 2, 3 lots of pi over 2. Alright, we want that one. So 3 pi over 2 minus 2 pi, well that's 4 over 2 pi, is minus pi over 2, which is what that angle is. So z to the power 10 is equal to 2 to the 15 times exp I minus pi over 2. Great! If you wrote this down, you would also be technically correct. What is this? 2 to the 15. Well, that can't be simplified anymore. This is cos minus pi over 2 plus I sine minus pi over 2, 2 pi, and so here I have to draw little diagrams. So here's my cos diagram. Minus pi over 2 is 0, so that's 0, and sine is, it starts there, and goes down, so it's minus 1, so that's minus I, so this is minus 2 to the 15i. Also a correct answer, just different ways of writing it. Now, from that, hopefully you saw that for all z an element of C, the modulus of z to the n is equal to, the modulus of z to the n is equal to the modulus of z to the n, and that n times the argument of z is an argument for z to the n. Yeah, prove it. This is another little lemma in the notes. Prove it. Okay, just like we've done for everything else, what are the real parts and imaginary parts? I'm not going to write it down. You do it. You do it. You've seen calculations of this. Okay, so now roots. So w and z be an element of C, and if w to the n equals z, then w is an nth root of z. So this works on the idea that you can inverse this, right? So if wn equals 1, then w is an nth root of unity, 1 being the multiplicative unit. Right, so here's a vocative except we haven't really told you what z to the 1 over n is, but you can guess, right? We're going to work through the details. Okay, so z equals rei theta, w equals sei theta, wn equals z, implies that s to the n ein theta equals rei, sorry, that should be a phi, make that a phi theta, which of course implies that s to the n equals r, and n of phi equals theta, and we have to include some integer multiple of pi, because, you know, the argument isn't unique. Yep. So we have that s equals r to the 1 over n, and these are real numbers, so you know what that is. And theta is going to be, phi is going to be theta plus 2k pi over n. So let's consider this a little more. Phi equals theta plus 2k pi over n, which can be rewritten as theta over n plus 2k pi over n. So that's some angle, and that's something. This will increase in integer multiples of 2 pi only when k is a multiple of n. Otherwise we're increasing by less than a multiple of 2 pi, which would be a different answer. So for k, an element of 0, 1, 2, up to n minus 1, we get different answers. They all have the same modulus, but we have different angles, arguments. Right, if k equals n plus 1, see that what happens. We have theta over n plus k n plus 1 pi over n, theta over n plus, well, split this out, 2n pi over n plus 2 pi over n, theta over n plus 2 pi over n plus 2 pi. This is what happens when you plug k equals 1 into here. So k equals n plus 1 gives the same answer as k equals 1, and it's the same for all of them. So there are nth roots. This is related to the fundamental theorem of algebra that we talked about. Polynomial equation with degree n should have n roots. Well, here they are for a simple polynomial, but justification of. Okay, let's write this up as a theorem because it's pretty important. Okay, for z, an element of C, say z is equal to rei theta, and n inside the natural numbers. We're restricting here because we haven't really told you what powers are that aren't natural numbers. The complex number z has n distinct nth roots. These roots are omega k equal to r 1 over n times the exponent of I times theta plus 2k pi over n, right? 1 over n e I theta plus 2k pi over n. And this is a circumstance where I prefer x because I think you can write out. The interesting bit of this equation is the power of exponents, so why not just write it out? Okay, where k is an element of 0, 1, 2, n minus 1. There you go, that's a much better bracket than that one. Right, let's do an example. Sixth roots of z equal to minus 8. So I'm going to rewrite this as modulus angle, and that's going to be 8 times cos of pi plus I sine of pi. I'm hiding my working because I did it beforehand, but anyway, there's a minus 1 here, and we need to write minus 1 out. And of course, minus 1 is pi rotated from 1, which is where this all comes from. This means that wk is equal to 8 to the 1 over 6th of x of I times pi plus 2k pi over 6. So what is this? W0. This is square root 2 e I pi over 6, because that term goes away. Square root 2 e I pi over 2. Right? Our 1 in there, that adds up to 3 pi divided by 6, pi over 2. Square root e I 5 pi over 6 omega 3 equals square root pi e I 7 pi over 6. Try it out. Put a 3 in there. That's a 6. 7 pi over 6. 7 pi over 6. 3 pi over 2. E I 11 pi over 6. And we stop there because if we continue, if we do, for example, would just be equal to omega 0, the argument might be different, but they would still have the same principal argument. So just stop there. Let's draw a little diagram of this because diagrams are cool. Okay, so pi over 6. I need to divide this into 6. So I've got 2. If I divide this into thirds, right? 1, 2, 3, 4, 4, 5, 6. And I'll do the same here. So each angle here is a pi over 6, right? So let's pick that one. Let's say that's omega 0. The radius, the modulus here is square root over 2. Where does omega 1 go? That's pi over 2. So omega 1. So that's a gap of 2 pi over 6, right? So this is a gap of 2 pi over 6, or pi 1/3. What's the next one? 5 pi over 6. Well, that's 1, 2, 3, 4, 5 pi over 6. And oh look, there's 2 there as well. So that's 2 over 6. It's a third as well. 3 is 7. 1, 2, 3, 4, 5, 6, 7. Omega 3, 7. And then 3 pi over 2. Well, we know what that one is. That's 3 pi over 2, which is here. Right, because that could also be written as, if we wanted to. So that's omega 4, and then 11 pi over 6. Well, 2 pi would be minus 1 from that, so that's minus 1 minus pi over 6, so that's omega 5. And it's important to note that there is a gap of pi over 3, or 2 pi over 6, between all of these angles. And that's the usual situation that happens. It's a thing, there's a constant gap between these, and we can prove it. So consider exp I theta plus 2k pi over n. Now this is equal to, I have to get have to get this right. 1 over 1 over n. 1 over n exp I theta over n plus 2 k minus 1 plus 1 pi over n. 1 over n exp, and you can see what I'm doing. I'm trying to rewrite this in terms of k minus 1, omega of k minus 1. I theta over n plus 2k minus 1 over n plus I, because I'm taking it, expanding out the inner bracket, 2 pi over n, which equals r1 over n exp I theta over n plus 2, I forgot a pi, 2k minus 1 pi over n e I 2 pi over n omega k times e I 2 pi over n. And so for sixth roots, we have omega k equals omega k minus 1 e I 2 pi over 6, which is a pi over third, which is the angle we saw, because when you multiply by a complex number with modulus 1, it's a rotation by the angle, and we know what that angle is. Right. Great. Which is kind of cool. So let's do another example where I skip the maths and rely on this fact. I'm kind of cheating when I say I'm going to skip the maths, because I'm going to show where the points are in the plane, but I'm not going to tell you their values. You could work it out though. But anyway, I'm also going to cheat a little with the first one. Fifth roots of 32. Well, I know that 2 to the 5 equals 32, which means I know that one of the angles must be there, right? Because there's no theta in here. This is all real, so it must be on the real line, and so omega 0 is going to equal 2. Now I have to divide this up to 5, which I'm not good at. 1, 2, 4, 3, 4, 5, ignoring this line here. So fifth roots. The rotation is going to be by 2 pi over 5, right? So there. One, two. Yeah. I'm doing such a bad job of dividing this up by pi over 5. Sorry. 1, 2. 1, 2. Oh. 1, 2, 3, 4, 5, 6. Omega 3 is there. 1, 2. Omega 4 is there. 1, 2. So 5 points. They all have modulus 2, because we know that is 2, and we all know the angles that they have to make. Right, so I barely did any work at all. Magic. Wow. Anyway, point is, well, that rotation by a fixed angle means you can work out where the points are pretty easily. Don't give us this as an answer. Do the work to give us values in assignments. I'm just being a smartass. Right. And that is section 1.6. Hope you've enjoyed so far.